A photograph is shown of a parked car plugged into a charging station in a paved parking area. The parking area is situated in a wooded area. People are walking in the background in the park-like atmosphere. Figure 17. 1. Electric vehicles are powered by batteries, devices that harness the energy of spontaneous redox reactions. Credit: Modification of work by Robert Kausbaker. Chapter outline. 17. 1. Review of redox chemistry. 17. 2 galvanic cells. 17. 3 electrode and cell potentials. 17. 4 potential, free energy and equilibrium. 17. 5 batteries and fuel cells. 17. 6 corrosion. 17. 7 electrolysis. Another chapter in this text introduced the chemistry of reduction-oxidation redox reactions. This important reaction class is defined by changes in oxidation states for one or more reactant elements, and it includes a subset of reactions involving the transfer of electrons between reactant species. Around the turn of the 19th century, chemists began exploring ways these electrons could be transferred indirectly via an external circuit, rather than directly via intimate contact of redox reactants. In the 2 centuries since, the field of electrochemistry has evolved to yield significant insights on the fundamental aspects of redox chemistry, as well as a wealth of technologies ranging from industrial-scale metallurgical processes to robust, rechargeable batteries for electric vehicles. Figure 17. 1. In this chapter, the essential concepts of electrochemistry will be addressed. Learning objectives. By the end of this section, you will be able to describe defining traits of redox chemistry, identify the oxidant and reductant of a redox reaction, balance chemical equations for redox reactions using the half-reaction method. Since reactions involving electron transfer are essential to the topic of electrochemistry, a brief review of redox chemistry is provided here that summarizes and extends the content of an earlier text chapter. See chapter on reaction stoichiometry. Readers wishing additional review are referred to the text chapter on reaction stoichiometry. Oxidation numbers. By definition, a redox reaction is one that entails changes in oxidation number, or oxidation state, for one or more of the elements involved. The oxidation number of an element in a compound is essentially an assessment of how the electronic environment of its atoms is different in comparison to atoms of the pure element. By this description, the oxidation number of an atom in an element is equal to 0. For an atom in a compound, the oxidation number is equal to the charge the atom would have in the compound if the compound were ionic. Consequential to these rules, the sum of oxidation numbers for all atoms in a molecule is equal to the charge on the molecule. To illustrate this formalism, examples from the 2 compound classes, ionic and covalent, will be considered. Simple ionic compounds present the simplest examples to illustrate this formalism, since by definition the elements' oxidation numbers are numerically equivalent to ionic charges. Sodium chloride, NaCl, is comprised of Na plus cations and Cl minus anions, and so oxidation numbers for sodium and chlorine are +1 and -1, respectively. Calcium fluoride, Kf2, is comprised of Ka2 plus cations and F minus anions, and so oxidation numbers for calcium and fluorine are +2 and -1, respectively. Covalent compounds require a more challenging use of the formalism. Water is a covalent compound, whose molecules consist of 2 H atoms bonded separately to a central O atom via polar covalent O-H bonds. The shared electrons comprising an O-H bond are more strongly attracted to the more electronegative O atom, and so it acquires a partial negative charge in the water molecule, relative to an O atom in elemental oxygen. Consequently, H atoms in a water molecule exhibit partial positive charges compared to H atoms in elemental hydrogen. The sum of the partial negative and partial positive charges for each water molecule is 0, and the water molecule is neutral. Imagine that the polarization of shared electrons within the O-H bonds of water were 100% complete. The result would be transfer of electrons from H to O, and water would be an ionic compound comprised of O2- anions and H+ cations. And so, the oxidation numbers for oxygen and hydrogen in water are -2 and +1, respectively. Applying this same logic to carbon tetrachloride, CCl4, yields oxidation numbers of +4 for carbon and -1 for chlorine. In the nitrate ion, no -3. The oxidation number for nitrogen is +5, and that for oxygen is -2, summing to equal the 1- charge on the molecule. 1 natom plus 5 natom plus 3 odoms -2 odom equals +5 plus -6 equals -1. Balancing redox equations. The unbalanced equation below describes the decomposition of molten sodium chloride. NaCl, letter 1 D459 Na, letter 1 D459, plus Cl2, letter 1 D454, letter 1 D462, letter 1 D45B, letter 1 D44F, letter 1 D44E, letter 1 D459, letter 1 D44E. This reaction satisfies the criterion for redox classification. Since the oxidation number for Na is decreased from +1 to 0, it undergoes reduction, and that for Cl is increased from -1 to 0, it undergoes oxidation. The equation in this case is easily balanced by inspection, requiring stoichiometric coefficients of 2 for the NaCl and Na. 2 NaCl, letter 1 D459 2, Na letter 1 D459, plus Cl2, letter 1 D454, letter 1 D44F, letter 1 D44E, letter 1 D459, letter 1 D44E, letter 1 D45B, letter 1 D450. Redox reactions that take place in aqueous solutions are commonly encountered in electrochemistry, and many involve water or its characteristic ions, H+, AC and O-, AC, as reactants or products. In these cases, equations representing the redox reaction can be very challenging to balance by inspection, and the use of a systematic approach called the half-reaction method is helpful. This approach involves the following steps. Write skeletal equations for the oxidation and reduction half-reactions. Balance each half-reaction for all elements except H and O. Balance each half-reaction for O by adding H2O. Balance each half-reaction for H by adding H+. Balance each half-reaction for charge by adding electrons. If necessary, multiply one or both half-reactions so that the number of electrons consumed in one is equal to the number produced in the other. Add the two half-reactions and simplify. If the reaction takes place in a basic medium, add O ions the equation obtained in step 7 to neutralize the H+ ions. Add in equal numbers to both sides of the equation and simplify. The examples below demonstrate the application of this method to balancing equations for aqueous redox reactions. Example 17. 1. Balancing equations for redox reactions in acidic solutions. Write the balanced equation representing reaction between solid copper and nitric acid to yield aqueous copper, Roman 2, ions and nitrogen monoxide gas. Solution. Following the steps of the half-reaction method, write skeletal equations for the oxidation and reduction half-reactions. Oxidation, Cu letter 1 D460, Cu2 plus, letter 1 D44E, letter 1 D45E. Reduction, HNO3, letter 1 D44E, letter 1 D45E, no, letter 1 D454. Balance each half-reaction for all elements except H and O oxidation. Cu letter 1 D460, Cu2 plus, letter 1 D44E, letter 1 D45E. Reduction, HNO3, letter 1 D44E, letter 1 D45E, no, letter 1 D454. Balance each half-reaction for O by adding H2O. Oxidation, Cu letter 1 D460, Cu2 plus, letter 1 D44E, letter 1 D45E. Reduction, HNO3, letter 1 D44E, letter 1 D45E, no, letter 1 D454 plus 2, letter 1 D407 to letter 1 D40E, letter 1 D459. Balance each half reaction for H by adding H+. Oxidation, Cu letter 1d460, Cu2+, letter 1d44e, letter 1d45e. Reduction, 3 letter 1d407 plus, letter 1d44e, letter 1d45e, plus HNO 3 letter 1d44e, letter 1d45e no, letter 1d454 plus 2 H2O, letter 1d459. Balance each half reaction for charge by adding electrons. Oxidation, Cu letter 1d460, Cu2 plus, letter 1d44e, letter 1d45e, plus 2 letter 1d41e minus. Reduction, 3 letter 1d41e minus plus 3H plus, letter 1d44e, letter 1d45e, plus HNO3, letter 1d44e, letter 1d45e no, letter 1d454 plus 2 H2O, letter 1d459. If necessary, multiply one or both half reactions so that the number of electrons consumed in one is equal to the number produced in the other. Oxidation times 3. 3 Cu letter 1d460, 3 Cu2 plus, letter 1d44e, letter 1d45e, plus 62e minus. Reduction times 2. 63e minus plus 63H plus, letter 1d44e, letter 1d45e, plus 2 HNO3, letter 1d44e, letter 1d45e to no, letter 1d454, plus 42 H2O, letter 1d459. Add the two half reactions and simplify. 3 Cu letter 1d460, plus 6 letter 1d41e minus plus 6H plus, letter 1d44e, letter 1d45e, plus 2 HNO3, letter 1d44e, letter 1d45e3, Cu2 plus, letter 1d44e, letter 1d45e, plus 6 letter 1d41e minus plus 2 no letter 1d454, plus 4 H2O, letter 1d459. 3 Cu letter 1d460, plus 6H plus, letter 1d44e, letter 1d45e, plus 2 HNO3, letter 1d44e, letter 1d45e, 3 Cu2 plus, letter 1d44e, letter 1d45e, plus 2 no, letter 1d454, plus 4 H2O, letter 1d459. If the reaction takes place in a basic medium, add O ions the equation obtained in step 7 to neutralize the H plus ions. Add in equal numbers to both sides of the equation, and simplify. This step not necessary, since the solution is stipulated to be acidic. The balanced equation for the reaction in an acidic solution is then 3 Cu letter 1d460, plus 6H plus, letter 1d44e, letter 1d45e, plus 2 HNO3, letter 1d44e, letter 1d45e, 3 Cu2 plus, letter 1d44e, letter 1d45e, plus 2 no, letter 1d454, plus 4 H2O, letter 1d459. Check your learning. The reaction above results when using relatively diluted nitric acid. If concentrated nitric acid is used, nitrogen dioxide is produced instead of nitrogen monoxide. Write a balanced equation for this reaction. Answer: Cu letter 1d460, plus 2H plus, letter 1d44e, letter 1d45e, plus 2 HNO3, letter 1d44e, letter 1d45e, Cu2 plus letter 1d44e, letter 1d45e, plus 2 no 2, letter 1d454 plus 2 H2O, letter 1d459. Example 17. 2. Balancing equations for redox reaction in basic solutions. Write the balanced equation representing reaction between aqueous permanganate ion, MnO4-, and solid chromium, Roman 3, hydroxide, Cr, O3 to yield solid manganese, Roman 4, oxide, MnO2, and aqueous chromate ion, CrO42-. The reaction takes place in a basic solution. Solution. Following the steps of the half-reaction method, write skeletal equations for the oxidation and reduction half-reactions. Oxidation, CrO3, letter 1d460, CrO42-, letter 1d44e, letter 1d45e. Reduction, MnO4-, letter 1d44e, letter 1d45e, MnO2, letter 1d460. Balance each half-reaction for all elements except H and O oxidation. CrO3, letter 1d460, CrO42-, letter 1d44e, letter 1d45e. Reduction, MnO4 minus, letter 1d44e, letter 1d45e. MnO2, letter 1d460. Balance each half reaction for O by adding H2O. Oxidation, H2 letter 1d40e, letter 1d459 plus CrO3, letter 1d460 CrO42 minus, letter 1d44e, letter 1d45e. Reduction, MnO4 minus, letter 1d44e, letter 1d45e, MnO2, letter 1d460, plus 2, letter 1d407 to letter 1d40e, letter 1d459. Balance each half reaction for H by adding H+. Oxidation, H2O, letter 1d459, plus CrO3, letter 1d460, CrO42 minus, letter 1d44e, letter 1d45e, plus 5, letter 1d407 plus, letter 1d44e, letter 1d45e. Reduction, 4, letter 1d407 plus, letter 1d44e, letter 1d45e, plus MnO4 minus, letter 1d44e, letter 1d45e, MnO2, letter 1d460, plus 2H2O, letter 1d459. Balance each half reaction for charge by adding electrons. Oxidation, H2O, letter 1d459, plus CrO3, letter 1d460, CrO42 minus, letter 1d44e, letter 1d45e, plus 5H plus, letter 1d44e, letter 1d45e, plus 3, letter 1d41e minus. Reduction, 3, letter 1d41e minus plus 4H plus, letter 1d44e, letter 1d45e, plus MnO4 minus, letter 1d44e, letter 1d45e, MnO2, letter 1d460, plus 2H2O, letter 1d459. If necessary, multiply one or both half reactions so that the number of electrons consumed in one is equal to the number produced in the other. This step is not necessary since the number of electrons is already in balance. Add the two half reactions and simplify. H2, letter 1d40e, letter 1d459 plus CrO3, letter 1d460, plus 3, letter 1d41e minus plus 4, letter 1d407 plus letter 1d44e, letter 1d45e, plus MnO4 minus, letter 1d44e, letter 1d45e, CrO42 minus, letter 1d44e, letter 1d45e, plus 5H plus, letter 1d44e, letter 1d45e, plus 3, letter 1d41e minus plus Mn2O, letter 1d459, CrO3, letter 1d460, plus MnO4 minus, letter 1d44e, letter 1d45e, CrO42 minus, letter 1d44e, letter 1d45e, plus H plus, letter 1d44e, letter 1d45e, plus MnO2, letter 1d460, plus H2O, letter 1d459. If the reaction takes place in a basic medium, add O ions the equation obtained in step 7 to neutralize the H plus ions. Add in equal numbers to both sides of the equation and simplify. Letter 1d40, letter 1d407 minus, letter 1d44e, letter 1d45e, plus CrO3, letter 1d460 plus MnO4 minus, letter 1d44e, letter 1d45e, CrO42 minus, letter 1d44e, letter 1d45e plus H plus, letter 1d44e, letter 1d45e, plus letter 1d40, letter 1d407 minus, letter 1d44e, letter 1d45e plus MnO2. 2O, letter 1d459. O minus, letter 1d44e, letter 1d45e, plus CrO3, letter 1d460, plus MnO4 minus, letter 1d44e, letter 1d45e, CrO42 minus, letter 1d44e, letter 1d45e, plus MnO2, letter 1d460, plus 2H2O, letter 1d459. Check your learning. Aqueous permanganate ion may also be reduced using aqueous bromide ion. Br minus, the products of this reaction being solid manganese, Roman 4, oxide and aqueous bromate ion, BrO3 minus. Write the balanced equation for this reaction occurring in a basic medium. Answer: H2O, letter 1d459, plus 2 MnO4 minus, letter 1d44e, letter 1d45e, plus Br minus, letter 1d44e, letter 1d45e, 2 MnO2, letter 1d460, plus BrO3 minus, letter 1d44e, letter 1d45e, plus 2O minus, letter 1d44e, letter 1d45e. Learning objectives. By the end of this section, you will be able to describe the function of a galvanic cell and its components. Use cell notation to symbolize the composition and construction of galvanic cells. As demonstration of spontaneous chemical change, Figure 17. 2 shows the result of immersing a coiled wire of copper into an aqueous solution of silver nitrate. A gradual but visually impressive change spontaneously occurs as the initially colorless solution becomes increasingly blue, and the initially smooth copper wire becomes covered with a porous gray solid. This figure includes 3 photographs. In the first, a test tube containing a clear, colorless liquid is shown with a loosely coiled copper wire outside the test tube to its right. In the second, the wire has been submerged in the clear, colorless liquid in the test tube, and the surface of the wire is darkened. In the third, the liquid in the test tube is bright blue-green. The wire in the solution appears dark near the top, and a gray, fuzzy material is present at the bottom of the test tube on the lower portion of the copper coil, giving a murky appearance to the liquid near the bottom of the test tube. Figure 17. 2. A copper wire and an aqueous solution of silver nitrate left are brought into contact center, and a spontaneous transfer of electrons occurs, creating blue Cu2+, Ac and gray Ag-S. Right. These observations are consistent with I. The oxidation of elemental copper to yield copper, Roman 2 ions, Cu2+, Ac, which impart a blue color to the solution, and Roman 2, the reduction of silver, I ions to yield elemental silver, which deposits as a fluffy solid on the copper wire surface. And so, the direct transfer of electrons from the copper wire to the aqueous silver ions is spontaneous under the employed conditions. A summary of this redox system is provided by these equations. Overall reaction. Oxidation half reaction, reduction half reaction. Cu letter 1d460 plus 2 Ag plus letter 1d44 letter 1d45e Cu 2 plus letter 1d44 letter 1d45e plus 2 Ag letter 1d460 Cu letter 1d460 Cu 2 plus letter 1d44 letter 1d45e plus 2 E minus 2 Ag plus letter 1d44 letter 1d45e plus 2 E minus 2 Ag letter 1d460. Consider the construction of a device that contains all the reactants and products of a redox system like the one here, but prevents physical contact between the reactants. Direct transfer of electrons is, therefore, prevented. Transfer, instead, takes place indirectly through an external circuit that contacts the separated reactants. Devices of this sort are generally referred to as electrochemical cells, and those in which a spontaneous redox reaction takes place are called galvanic cells or voltaic cells. A galvanic cell based on the spontaneous reaction between copper and silver, I, is depicted in Figure 17. 3. The cell is comprised of 2 half cells, each containing the redox conjugate pair, couple, of a single reactant. The half cell shown at the left contains the Cu0/Cu, Roman 2, couple in the form of a solid copper foil and an aqueous solution of copper nitrate. The right half cell contains the I/Ag0, couple as solid silver foil and an aqueous silver nitrate solution. An external circuit is connected to each half cell at its solid foil, meaning the Cu and Ag foil each function as an electrode. By definition, the anode of an electrochemical cell is the electrode at which oxidation occurs, in this case, the Cu foil, and the cathode is the electrode where reduction occurs, the Ag foil. The redox reactions in a galvanic cell occur only at the interface between each half cell's reaction mixture and its electrode. To keep the reactants separate while maintaining charge balance, the 2 half-cell solutions are connected by a tube filled with inert electrolyte solution called a salt bridge. The spontaneous reaction in this cell produces Cu2 plus cations in the anode half cell and consumes Ag plus ions in the cathode half cell, resulting in a compensatory flow of inert ions from the salt bridge that maintains charge balance. Increasing concentrations of Cu2+ in the anode half cell are balanced by an influx of NO3- from the salt bridge, while a flow of Na+ into the cathode half cell compensates for the decreasing Ag+ concentration. This figure contains a diagram of an electrochemical cell. Two beakers are shown. Each is just over half full. The beaker on the left contains a blue solution and is labeled below as 1 m solution of copper, II nitrate Cu, NO subscript 3 subscript 2. The beaker on the right contains a colorless solution and is labeled below as 1 m solution of silver nitrate, a GNO subscript 3. A glass tube in the shape of an inverted U connects the two beakers at the center of the diagram. The tube contents are colorless. The ends of the tubes are beneath the surface of the solutions in the beakers, and a small gray plug is present at each end of the tube. The plug in the left beaker is labeled porous plug. At the center of the diagram, the tube is labeled salt bridge, NaNO subscript 3. Each beaker shows a metal strip partially submerged in the liquid. The beaker on the left has an orange-brown strip that is labeled Cu anode negative at the top. The beaker on the right has a silver strip that is labeled a G cathode positive at the top. A wire extends from the top of each of these strips to a rectangle indicating external circuit that is labeled flow of electrons with an arrow pointing to the right following. A curved arrow extends from the Cu strip into the surrounding solution. The tip of this arrow is labeled Cu superscript 2+. A curved arrow extends from the salt bridge into the beaker on the left into the blue solution. The tip of this arrow is labeled NO subscript 3 superscript negative. A curved arrow extends from the solution in the beaker on the right to the G strip. The base of this arrow is labeled a G superscript plus. A curved arrow extends from the colorless solution to salt bridge in the beaker on the right. The base of this arrow is labeled NO subscript 3 superscript negative. Just right of the salt bridge in the colorless solution is the label N, a superscript plus. Just above this region of the tube appears the label flow of cations. Just left of the salt bridge in the blue solution is the label NO subscript 3 superscript negative. Just above this region of the tube appears the label flow of anions. Figure 17. 3. A galvanic cell based on the spontaneous reaction between copper and silver, ions. Cell notation. Abbreviated symbolism is commonly used to represent a galvanic cell by providing essential information on its composition and structure. These symbolic representations are called cell notations or cell schematics, and they are written following a few guidelines. The relevant components of each half cell are represented by their chemical formulas or element symbols. All interfaces between component phases are represented by vertical parallel lines. If two or more components are present in the same phase, their formulas are separated by commas. By convention, the schematic begins with the anode and proceeds left to right identifying phases and interfaces encountered within the cell, ending with the cathode. A verbal description of the cell as viewed from anode to cathode is often a useful first step in writing its schematic. For example, the galvanic cell shown in Figure 17. 3 consists of a solid copper anode immersed in an aqueous solution of copper, Roman 2 nitrate that is connected via a salt bridge to an aqueous silver, I nitrate solution, immersed in which is a solid silver cathode. Converting this statement to symbolism, following the above guidelines results in the cell schematic. Q letter 1D460. 1 letter 1D440 Cu. No 3 2 letter 1D440 letter 1D45E 1 letter 1D440. Ag no 3. Letter 1D440 letter 1D45E Ag letter 1D460. Consider a different galvanic cell. See Figure 17. 4. Based on the spontaneous reaction between solid magnesium and aqueous iron, Roman 3, ions. Net cell reaction. Oxidation half reaction. Reduction half reaction. Mg letter 1d460 plus 2Fe3 plus letter 1d44 letter 1d45e Mg 2 plus letter 1d44 letter 1d45e plus 2Fe2 plus letter 1d44 letter 1d45e Mg letter 1d460 Mg2 plus letter 1d44 letter 1d45e plus 2e minus 2Fe3 plus letter 1d44 letter 1d45e plus 2e minus 2Fe2 plus letter 1d44 letter 1d45. In this cell, a solid magnesium anode is immersed in an aqueous solution of magnesium chloride that is connected via a salt bridge to an aqueous solution containing a mixture of iron Roman 3 chloride and iron Roman 2 chloride, immersed in which is a platinum cathode. The cell schematic is then written as Mg letter 1d4600, 1 letter 1d440, MgCl2, letter 1d44 letter 1d45e0, 2 letter 1d440 FeCl3, letter 1d44 letter 1d45e, 0, 3 letter 1d440 FeCl2, letter 1d44 letter 1d45e PT, letter 1d460. Notice the cathode half cell is different from the others considered thus far in that its electrode is comprised of a substance, PT, that is neither a reactant nor a product of the cell reaction. This is required when neither member of the half cell's redox couple can reasonably function as an electrode, which must be electrically conductive and in a phase separate from the half cell solution. In this case, both members of the redox couple are solute species, and so PT is used as an inert electrode that can simply provide or accept electrons to redox species in solution. Electrodes constructed from a member of the redox couple, such as the Mg anode in this cell, are called active electrodes. This figure contains a diagram of an electrochemical cell. 2 beakers are shown. Each is just over half full. The beaker on the left contains a colorless solution. The beaker on the right also contains a colorless solution. A glass tube in the shape of an inverted U connects the 2 beakers at the center of the diagram. The tube contents are colorless. The ends of the tubes are beneath the surface of the solutions in the beakers, and a small gray plug is present at each end of the tube. At the center of the diagram, the tube is labeled salt bridge. Each beaker shows a metal coil submerged in the liquid. The beaker on the left has a thin, gray, coiled strip that is labeled Mg anode. The beaker on the right has a black wire that is oriented horizontally and coiled up in a spring-like appearance that is labeled PT cathode. Below the coil is the label Fe superscript 3+, with a curved right arrowing pointing from that to the label Fe superscript 2+. A wire extends across the top of the diagram that connects the ends of the Mg strip and PT cathode just above the opening of each beaker. At the center of the wire above the 2 beakers is a rectangle labeled external circuit. Above the rectangle is the label flow of electrons, followed by a right-pointing arrow. An arrow points down and to the right from the label N, a superscript plus, at the upper right region of the salt bride. An arrow points down and to the left from the label Cl superscript negative at the upper left region of the salt bride. Below the gray lug at the left end of the salt bridge in the surrounding solution in the left beaker is the label Cl superscript negative. Below the coil on this side is a right arrow and the label Mg superscript 2+. The label 01M MgCl subscript 2 appears beneath the left beaker. The label 02M FeCl subscript 3 and 03M FeCl subscript 2 appears beneath the right beaker. Figure 17. For a galvanic cell based on the spontaneous reaction between magnesium and iron Roman 3 ions. Example 17. 3. Writing galvanic cell schematics. A galvanic cell is fabricated by connecting 2 half cells with a salt bridge, one in which a chromium wire is immersed in a 1mCrCl3 solution, and another in which a copper wire is immersed in 1mCuCl2. Assuming the chromium wire functions as an anode, Write the schematic for this cell along with equations for the anode half reaction, the cathode half reaction, and the overall cell reaction. Solution. Since the chromium wire is stipulated to be the anode, the schematic begins with it and proceeds left to right, symbolizing the other cell components until ending with the copper wire cathode. CR letter 1D460, 1 letter 1D440, CrCl3, letter 1D440, letter 1D45E, 1 letter 1D440, QCl2 letter 1D440, letter 1D45E, Q letter 1D460. The half reactions for this cell are anode oxidation, cathode reduction, Cr letter 1D460, Cr3 plus, letter 1D440, letter 1D45E, plus 3E minus Q2 plus, letter 1D440, letter 1D45E, plus 2E minus Q, letter 1D460. Multiplying to make the number of electrons lost by Cr and gained by Q2 plus equal yields. Anode oxidation, cathode reduction, 2Cr, letter 1D460 Cr3 plus, letter 1D440, letter 1D45E, plus 6E minus 3 Q2 plus, letter 1D440, letter 1D45E, plus 6E minus 3 Q, letter 1D460. Adding the half reaction equations and simplifying yields an equation for the cell reaction. 2Cr, letter 1D460, plus 3Q2 plus, letter 1D440, letter 1D45E2, Cr3 plus, letter 1D440, letter 1D45E, plus 3Q, letter 1D460. Check your learning, omitting solute concentrations and spectator ion identities. Write the schematic for a galvanic cell whose net cell reaction is shown below. SN4 plus, letter 1D440, letter 1D45E, plus ZN, letter 1D460. SN2 plus, letter 1D440, letter 1D45E, plus ZN2 plus, letter 1D440, letter 1D45E. Answer. ZN2 plus, letter 1D440, letter 1D45E, SN4 plus, letter 1D440, letter 1D45E. SN2 plus, letter 1D440, letter 1D45E, PT, letter 1D460. Learning objectives. By the end of this section, you will be able to describe and relate the definitions of electrode and cell potentials, interpret electrode potentials in terms of relative oxidant and reductant strengths, calculate cell potentials, and predict redox spontaneity using standard electrode potentials, unlike the spontaneous oxidation of copper by aqueous silver ions described in section 17. 2. Immersing a copper wire in an aqueous solution of lead Roman II ions yields no reaction. The two species, Ag plus, AC, and Pb2 plus, AC, thus show a distinct difference in their redox activity towards copper. The silver ion spontaneously oxidized copper, but the lead ion did not. Electrochemical cells permit this relative redox activity to be quantified by an easily measured property, potential. This property is more commonly called voltage when referenced in regard to electrical applications, and it is a measure of energy accompanying the transfer of charge. Potentials are measured in the volt unit, defined as 1 joule of energy per 1 coulomb of charge, V equals Jc. When measured for purposes of electrochemistry, a potential reflects the driving force for a specific type of charge transfer process, namely, the transfer of electrons between redox reactants. Considering the nature of potential in this context, it is clear that the potential of a single half cell or a single electrode can't be measured. Transfer of electrons requires both a donor and recipient, in this case, a reductant and an oxidant respectively. Instead, a half-cell potential may only be assessed relative to that of another half-cell. It is only the difference in potential between two half-cells that may be measured, and these measured potentials are called cell potentials. SL, defined as SL equals ecathode minus enode, where ecathode and enode are the potentials of two different half-cells functioning as specified in the subscripts. As for other thermodynamic quantities, the standard cell potential, E degrees cell, is a cell potential measured when both half cells are under standard state conditions, 1 m concentrations, 1 bar pressures, 298 K. E degrees cell equals E degrees cathode minus E degrees anode to simplify the collection and sharing of potential data for half reactions. The scientific community has designated one particular half cell to serve as a universal reference for cell potential measurements, assigning it a potential of exactly 0 V. This half cell is the standard hydrogen electrode, SHE, and it is based on half reaction below. 2H plus, letter 1D44E, letter 1D45E, plus 2E minus H2, letter 1D454. A typical SHE contains an inert platinum electrode immersed in precisely 1 m aqueous H+, and a stream of bubbling H2 gas at 1 bar pressure, all maintained at a temperature of 298 K, see Figure 17. 5. The figure shows a beaker just over half full of a blue liquid. A glass tube is partially submerged in the liquid. Bubbles, which are labeled H subscript 2 G, are rising from the dark grayquare, labeled PT electrode at the bottom of the tube. Below the bottom of the tube pointing to the solution in the beaker is the label 1mH superscript plus a Q. A curved arrow points up to the right, indicating the direction of the bubbles. A black wire, which is labeled PT wire, extends from the dark gray air up the interior of the tube through a small port at the top. A second small port extends out the top of the tube to the left. An arrow points to the port opening from the left. The base of this arrow is labeled H subscript 2 G at 1 atm. A light gray points to a diagram in a circle at the right that illustrates the surface of the PT electrode in a magnified view. PT atoms are illustrated as a uniform cluster of gray which are labeled PT electrode atoms. On the gray atographs, the label E superscript negative is shown 4 times in a nearly even vertical distribution to show electrons on the PT surface. A curved arrow extends from a white sphere labeled H superscript plus at the right of the PT atoms to the uppermost electron shown. Just below, a straight arrow extends from the PT surface to the right to a pair of linked white spheres which are labeled H subscript 2. A curved arrow extends from a second white sphere labeled H superscript plus at the right of the PT atoms to the second electron shown. A curved arrow extends from the third electron on the PT surface to the right to a white sphere labeled H superscript plus. Just below, an arrow points left from a pair of linked white spheres which are labeled H subscript 2 to the PT surface. A curved arrow extends from the fourth electron on the PT surface to the right to a white sphere labeled H superscript plus. Figure 17. 5. A standard hydrogen electrode, SHE. The assigned potential of the SHE permits the definition of a conveniently measured potential for a single half cell. The electrode potential X for a half cell X is defined as the potential measured for a cell comprised of X acting as cathode and the SHE acting as anode. SL equals X minus SH equals 0 V. Defined. SL equals EX when the half cell X is under standard state conditions. Its potential is the standard electrode potential, E degrees X. Since the definition of cell potential requires the half cells function as cathodes, these potentials are sometimes called standard reduction potentials. This approach to measuring electrode potentials is illustrated in Figure 17. 6, which depicts a cell comprised of an SHE connected to a copper, copper, half cell under standard state conditions. A voltmeter in the external circuit allows measurement of the potential difference between the two half cells. Since the Q half cell is designated as the cathode in the definition of cell potential, it is connected to the red, positive, input of the voltmeter, while the designated SHE anode is connected to the black, negative, input. These connections ensure that the sign of the measured potential will be consistent with the sign conventions of electrochemistry per the various definitions discussed above. A cell potential of +0. 337V is measured, and so E degrees cell equals E degrees Q equals plus 0. 337V tabulations of E degrees values for other half-cells measured in a similar fashion are available as reference literature to permit calculations of cell potentials and the prediction of the spontaneity of redox processes. This figure contains a diagram of an electrochemical cell. Two beakers are shown. Each is just over half full. The beaker on the left contains a clear, colorless solution and is labeled below as 1mH superscript plus. The beaker on the right contains a blue solution and is labeled below as 1mCu superscript 2 plus. A glass tube in the shape of an inverted U connects the two beakers at the center of the diagram. The tube contents are colorless. The ends of the tubes are beneath the surface of the solutions in the beakers, and a small gray lug is present at each end of the tube. The beaker on the left has a glass tube partially submersed in the liquid. Bubbles are rising from the gray square, labeled standard hydrogen electrode at the bottom of the tube. A curved arrow points up to the right, indicating the direction of the bubbles. A black wire extends from the gray square up the interior of the tube through a small port at the top to a rectangle with a digital readout of positive 0. 337V, which is labeled voltmeter. A second small port extends out the top of the tube to the left. An arrow points to the port opening from the left. The base of this arrow is labeled 1atmH subscript 2 G. The beaker on the right has an orange-brown strip that is labeled Cu electrode at the top. A wire extends from the top of this strip to the voltmeter. An arrow points toward the voltmeter from the left, which is labeled E superscript negative flow. Similarly, an arrow points away from the voltmeter to the right. A curved arrow extends from the surrounding solution to the standard hydrogen electrode in the beaker. The end of the arrow is labeled H subscript 2, and tip of this arrow is labeled 2H superscript plus. A curved arrow extends from the Cu superscript 2 plus label in the solution to a Cu label at the lower edge of the Cu electrode. Between the two beakers is the label T equals 298K. Figure 17. 6. A cell-permitting experimental measurement of the standard electrode potential for the half-reaction Q2 plus, letter 1D44E letter 1D45E, plus 2E minus Q, letter 1D460, table 17. 1 provides a listing of standard electrode potentials for a selection of half-reactions in numerical order, and a more extensive alphabetical listing is given in Appendix L. Selected standard reduction potentials at 25 degrees C half-reaction E degrees V, F2, letter 1D454, plus 2E minus 2F minus, letter 1D44E letter 1D45E, plus 2. 866 PbO2, letter 1D460, plus So 42 minus, letter 1D44E letter 1D45E, plus 4H plus, letter 1D44E letter 1D45E, plus 2E minus Pb So 4, letter 1D460, plus 2H2O, letter 1D459, plus 1. 69 MnO4 minus, letter 1D44E letter 1D45E, plus 8H plus, letter 1D44E letter 1D45E, plus 5E minus Mn2 plus, letter 1D44E letter 1D45E plus 4H2O letter 1D459 plus 1. 507 O3 plus, letter 1D44E letter 1D45E, plus 3E minus O letter 1D460 plus 1. 498 Cl2 letter 1D454, plus 2E minus 2 Cl minus, letter 1D44E letter 1D45E, plus 1. 35,827 O2, letter 1D454, plus 4H plus, letter 1D44E letter 1D45E, plus 4E minus 2H2O, letter 1D459 plus 1. 229 PT2 plus, letter 1D44E letter 1D45E, plus 2E minus PT, letter 1D460 plus 1. 20 BR2, letter 1D44E letter 1D45E, plus 2E minus 2BR minus, letter 1D44E, letter 1D45E, plus 1. 873 Ag plus, letter 1D44E, letter 1D45E, plus E minus Ag, letter 1D460, plus 0, 7996 HG22 plus, letter 1D44E, letter 1D45E, plus 2E minus 2 HG, letter 1D459 plus 0. 7973 Phi 3 plus, letter 1D44E, letter 1D45E, plus E minus Phi 2 plus, letter 1D44E, letter 1D45E, plus 0. 771 MN04 minus, letter 1D44E, letter 1D45E, plus 2H2O, letter 1D459, plus 3E minus MN02, letter 1D460, plus 4O minus, letter 1D44E, letter 1D45E, plus 0. 558 I2, letter 1D460, plus 2E minus 2I minus, letter 1D44E, letter 1D45E, plus 0. 5355 902, letter 1D460, plus 2H2O, letter 1D459, plus 2E minus 902, letter 1D460, plus 2O minus, letter 1D44E, letter 1D45E, plus 0. 49 Q2 plus, letter 1D44E, letter 1D45E, plus 2E minus Q, letter 1D460, plus 034 Hg to Cl2, letter 1D460, plus 2E minus 2 Hg, letter 1D459, plus 2 Cl minus, letter 1D44E, letter 1D45E, plus 0. 26,808 Ag Cl, letter 1D460, plus E minus Ag, letter 1D460, plus Cl minus, letter 1D44E, letter 1D45E, plus 0. 22,233 SN4 plus, letter 1D44E, letter 1D45E, plus 2E minus SN2 plus, letter 1D44E, letter 1D45E, plus 0. 151 2H plus, letter 1D44E, letter 1D45E, plus 2E minus H2, letter 1D454, 0, PB2 plus, letter 1D44E, letter 1D45E, plus 2E minus PB, letter 1D460, minus 0. 1262 SN2 plus, letter 1D44E, letter 1D45E, plus 2E minus SN, letter 1D460, minus 0. 1375 Ni2 plus, letter 1D44E, letter 1D45E, plus 2E minus Ni, letter 1D460, minus 0. 257 Co 2 plus, letter 1D44E, letter 1D45E, plus 2E minus Co, letter 1D460, minus 0. 28 PB So 4, letter 1D460, plus 2E minus PB, letter 1D460, plus So 42 minus, letter 1D44E, letter 1D45E, minus 0. 3505 CD2 plus, letter 1D44E, letter 1D45E, plus 2E minus CD, letter 1D460, minus 0. 4030 Phi 2 plus, letter 1D44E, letter 1D45E, plus 2E minus Phi, letter 1D460, minus 0. 447 CR3 plus, letter 1D44E, letter 1D45E, plus 3E minus CR, letter 1D460, minus 0. 744 MN2 plus, letter 1D44E, letter 1D45E, plus 2E minus MN, letter 1D460, minus 1. 185 ZN, O2, letter 1D460, plus 2E minus ZN, letter 1D460, plus 2O minus, letter 1D44E, letter 1D45E, minus 1. 245 ZN2 plus, letter 1D44E, letter 1D45E, plus 2E minus ZN, letter 1D460, minus 0. 7618 Al3 plus, letter 1D44E, letter 1D45E, plus 3E minus Al, letter 1D460, minus 1. 662 Mg2, letter 1D44E, letter 1D45E, plus 2E minus Mg, letter 1D460, minus 2. 372 Na plus, letter 1D44E, letter 1D45E, plus E minus Na, letter 1D460, minus 2. 71 Ka2 plus, letter 1D44E, letter 1D45E, plus 2E minus Ka, letter 1 D460 minus 2. 868 ba 2 plus, letter 1 D44 letter 1 D45E, plus 2E minus ba, letter 1 D460 minus 2. 912 K plus, letter 1 D44 letter 1 D45E plus E minus K, letter 1 D460 minus 2. 931 Li plus, letter 1 D44 letter 1 D45E plus E minus Li, letter 1 D460 minus 3. 4 Table 17. 1 Example 17. 4 Calculating standard cell potentials. What is the standard potential of the galvanic cell shown in Figure 17? 3. Solution the cell in Figure 17. 3 is galvanic, the spontaneous cell reaction involving oxidation of its copper anode and reduction of silver ions at its silver cathode. Cell reaction, anode half reaction, cathode half reaction. Q letter 1 D460 plus 2 ag plus letter 1 D44 letter 1 D45E Q 2 plus letter 1 D44 letter 1 D45E plus 2 ag letter 1 D460 Q letter 1 D460 Q 2 plus letter 1 D44 letter 1 D45E plus 2 E minus 2 ag plus letter 1 D44 letter 1 D45E plus 2 E minus 2 ag letter 1 D460. The standard cell potential computed as E degrees cell equals E degrees cathode minus E degrees anode, E degrees ag minus E degrees Q0. 7,996 V minus 0. 34 V plus 0, 46 V. Check your learning. What is the standard cell potential expected if the silver cathode half cell in Figure 17? 3 is replaced with a lead half cell, PB2 plus, letter 1D44 letter 1D45E, plus 2E minus PB, letter 1D460. Answer, minus 0. 47V, interpreting electrode and cell potentials, thinking carefully about the definitions of cell and electrode potentials, and the observations of spontaneous redox change presented thus far. A significant relation is noted. The previous section described the spontaneous oxidation of copper by aqueous silver ions, but no observed reaction with aqueous lead Roman II ions. Results of the calculations in example 17. 4 have just shown the spontaneous process is described by a positive cell potential, while the non-spontaneous process exhibits a negative cell potential. And so, with regard to the relative effectiveness, strength, with which aqueous Ag plus and Pb2 plus ions oxidize Cu under standard conditions, the stronger oxidant is the one exhibiting the greater standard electrode potential, E degrees. Since by convention electrode potentials are for reduction processes, an increased value of E degrees corresponds to an increased driving force behind the reduction of the species, hence increased effectiveness of its action as an oxidizing agent on some other species. Negative values for electrode potentials are simply a consequence of assigning a value of 0V to the SHE, indicating the reactant of the half reaction is a weaker oxidant than aqueous hydrogen ions. Applying this logic to the numerically ordered listing of standard electrode potentials in Table 17, one shows this listing to be likewise in order of the oxidizing strength of the half reaction's reactant species, decreasing from strongest oxidant, most positive E degrees, to weakest oxidant, most negative E degrees. Predictions regarding the spontaneity of redox reactions under standard state conditions can then be easily made by simply comparing the relative positions of their table entries. By definition, E degrees cell is positive when E degrees cathode, E degrees anode, and so any redox reaction in which the oxidant's entry is above the reductant's entry is predicted to be spontaneous. Reconsideration of the two redox reactions in example 17. 4 provides support for this fact. The entry for the silver, I/silver 0 half reaction is above that for the copper II copper half reaction, and so the oxidation of Cu by Ag plus is predicted to be spontaneous, E degrees cathode, E degrees anode, and so E degrees cell 0. Conversely, the entry for the lead Roman II/lead 0 half cell is beneath that for copper II, copper. And the oxidation of Cu by Pb2 plus is non-spontaneous, E degrees cathode, E degrees anode, and so E degrees cell 0. Recalling the chapter on thermodynamics, the spontaneities of the forward and reverse reactions of a reversible process show a reciprocal relationship. If a process is spontaneous in one direction, it is non-spontaneous in the opposite direction. As an indicator of spontaneity for redox reactions, the potential of a cell reaction shows a consequential relationship in its arithmetic sign. The spontaneous oxidation of copper by lead, Roman II, ions is not observed. Cu, letter 1d460, plus Pb2 plus, letter 1d44, letter 1d45e. Cu2 plus, letter 1d44, letter 1d45e, plus Pb, letter 1d460, letter 1d438 degrees, letter 1d453, letter 1d45c, letter 1d45f, letter 1d464, letter 1d44e, letter 1d45f equals minus 0. 47v, negative non-spontaneous, and so the reverse reaction, the oxidation of lead by copper, Roman II ions, is predicted to occur spontaneously. Pb, letter 1d460, plus Cu2 plus, letter 1d44, letter 1d45e Pb, 2 plus, letter 1d44, letter 1d45e, plus Cu, letter 1d460, letter 1d438 degrees, letter 1d453, letter 1d45c, letter 1d45f, letter 1d464, letter 1d44, letter 1d45f equals plus 0. 47v, positive, spontaneous. Note that reversing the direction of a redox reaction effectively interchanges the identities of the cathode and anode half reactions, and so the cell potential is calculated from electrode potentials in the reverse subtraction order than that for the forward reaction. In practice, a voltmeter would report a potential of minus 0. 47V with its red and black inputs connected to the Pb and Cu electrodes, respectively. If the inputs were swapped, the reported voltage would be plus 0.47V example 17. 5 predicting redox spontaneity are aqueous iron, Roman II ions predicted to spontaneously oxidize elemental chromium under standard state conditions. Assume the half reactions to be those available in Table 17. 1. Solution referring to the tabulated half reactions. The redox reaction in question can be represented by the equations below. Cr letter 1d460 plus Phe2 plus letter 1d44e letter 1d45e, Cr3 plus letter 1d44e letter 1d45e, plus Phe letter 1d460, the entry for the putative oxidant, Phe2 plus, appears above the entry for the reductant, Cr, and so a spontaneous reaction is predicted per the quick approach described above. Supporting this predication, by calculating the standard cell potential for this reaction, gives E degrees cell equals E degrees cathode minus E degrees anode E degrees Phe. Roman II minus E degrees Cr minus 0. 447V minus 0. 744V equals plus 0. 297V, the positive value for the standard cell potential, indicates the process is spontaneous under standard state conditions. Check your learning. Use the data in Table 17. 1. To predict the spontaneity of the oxidation of bromide ion by molecular iodine under standard state conditions, supporting the prediction by calculating the standard cell potential for the reaction. Repeat for the oxidation of iodide ion by molecular bromine. Answer. I2 letter 1d460 plus 2 Br minus letter 1d44 letter 1d45e 2I minus letter 1d44 letter 1d45e plus Br2 letter 1d459 Br2 letter 1d460 plus 2I minus letter 1d44 letter 1d45e 2 Br minus letter 1d44 letter 1d45e plus I2 letter 1d459 letter 1d438 degrees cell equals 0. 5518V non-spontaneous letter 1d438 degrees cell equals plus 0. 5518V spontaneous. Learning objectives. By the end of this section, you will be able to Explain the relations between potential, free energy change, and equilibrium constants. Perform calculations involving the relations between cell potentials, free energy changes, and equilibrium. Use the Nernst equation to determine cell potentials under non-standard conditions. So far in this chapter, the relationship between the cell potential and reaction spontaneity has been described. Suggesting a link to the free energy change for the reaction, see chapter on thermodynamics. The interpretation of potentials as measures of oxidant strength was presented, bringing to mind similar measures of acid-base strength as reflected in equilibrium constants. See the chapter on acid-base equilibria. This section provides a summary of the relationships between potential and the related thermodynamic properties delta and Ke degrees and delta degrees. The standard free energy change of a process, delta degrees, was defined in a previous chapter as the maximum work that could be performed by a system, Wmax. In the case of a redox reaction taking place within a galvanic cell under standard state conditions, essentially, all the work is associated with transferring the electrons from reductant to oxidant, Wellek. Delta letter 1d43a degrees equals letter 1d464 max equals letter 1d464 ELEC. The work associated with transferring electrons is determined by the total amount of charge, coulombs, transferred and the cell potential. Delta letter 1d43a degrees equals letter 1d464 ELEC. Delta letter 1d43a degrees equals minus letter 1d45b. Letter 1d439 letter 1d438 degrees cell, minus letter 1d45b, letter 1d439 letter 1d438 degrees cell, where N is the number of moles of electrons transferred, F is Faraday's constant, and E degrees cell is the standard cell potential. The relation between free energy change and standard cell potential confirms the sign conventions and spontaneity criteria previously discussed for both of these properties. Spontaneous redox reactions exhibit positive potentials and negative free energy changes, E degrees and K. Combining a previously derived relation between delta degrees and K, see the chapter on thermodynamics, and the equation above relating delta degrees and E degrees cell yields the following. Delta letter 1d438 degrees letter 1d438 degrees cell equals minus letter 1d445 letter 1d447 ln letter 1d43 equals minus letter 1d45b letter 1d439 letter 1d438 degrees cell letter 1d445 letter 1d447 letter 1d45b letter 1d439 ln letter 1d43. This equation indicates redox reactions with large, positive, standard cell potentials will proceed far towards completion, reaching equilibrium when the majority of reactant has been converted to product. A summary of the relations between E degrees, delta degrees, and K is depicted in Figure 17.7, and a table correlating reaction spontaneity to values of these properties is provided in Table 17. 2. A diagram is shown that involves three double-headed arrows positioned in the shape of an equilateral triangle. The vertices are labeled in red. The top vertex is labeled K. The vertex at the lower left is labeled delta G superscript degree symbol. The vertex at the lower right is labeled E superscript degree symbol subscript cell. The right side of the triangle is labeled E superscript degree symbol subscript cell equals RT divided by NF, LNK. The lower side of the triangle is labeled delta G superscript degree symbol equals negative NFE superscript degree symbol subscript cell. The left side of the triangle is labeled delta G superscript degree symbol equals negative RT LNK. Figure 17. 7 graphic depicting the relation between three important thermodynamic properties. K delta G degrees E degrees cell. 1-0. Reaction is spontaneous under standard conditions. Products more abundant at equilibrium. 1. Reaction is non-spontaneous under standard conditions. Reactants more abundant at equilibrium. Equals 1 equals 0 equals 0. Reaction is at equilibrium under standard conditions. Reactants and products equally abundant. Table 17. 2. Example 17. 6. Equilibrium constants, standard cell potentials, and standard free energy changes. Use data from Appendix L to calculate the standard cell potential, standard free energy change, and equilibrium constant for the following reaction at 25 degrees C. Comment on the spontaneity of the forward reaction and the composition of an equilibrium mixture of reactants and products. 2 Ag plus, letter 1D44E, letter 1D45E, plus Phi, letter 1D4602, Ag letter 1D460, plus Phi 2 plus letter 1D44E, letter 1D45E. Solution. The reaction involves an oxidation-reduction reaction, so the standard cell potential can be calculated using the data in Appendix L. Anode oxidation, cathode reduction. Phi, letter 1D460, Phi 2 plus, letter 1D44E, letter 1D45E, plus 2E minus 2 times Ag plus, letter 1D44E, letter 1D45E, plus E minus Ag letter 1D460. Letter 1D438 cell equals letter 1D438 cathode minus letter 1D438 anode equals letter 1D438 Phi 2 plus slash Phi letter 1D438 Ag plus slash Ag letter 1D438 Ag plus slash Ag minus letter 1D43. 447 V0, 7996 V plus 1, 247 V. With n equals 2, the equilibrium constant is then letter 1D438 cell, letter 1D43, letter 1D43, letter 1D43, letter 1D43 equals 0. 592 V letter 1D45B log, letter 1D43E 10, letter 1D45B times letter 1D438 cell slash 0. 592 V 102 times 1. 247 V0. 592 V 1042. 1281. 3 times 1042. The standard free energy is then delta letter 1D43A, delta letter 1D43A, degrees equals minus letter 1D45B, letter 1D439, letter 1D438 cell minus 2 times 96, 485 Cmol times 1. 247 JC equals minus 240, 6 kJ mol. The reaction is spontaneous, as indicated by a negative free energy change and a positive cell potential. The K value is very large, indicating the reaction proceeds to near completion to yield an equilibrium mixture containing mostly products. Check your learning. What is the standard free energy change and the equilibrium constant for the following reaction at room temperature? Is the reaction spontaneous? Sn, letter 1D460, plus 2Q2 plus, letter 1D44E, letter 1D45E, Sn2 plus, letter 1D44E, letter 1D45E, plus 2Q plus, letter 1D44E, letter 1D45E. Answer. Spontaneous. N equals 2, letter 1D438 cell equals plus 0, 291 V, delta letter 1D43A degrees equals minus 56, 2 kJ mol. K equals 6. 8 times 109. Potentials at non-standard conditions, the Nernst equation. Most of the redox processes that interest science and society do not occur under standard state conditions, and so the potentials of these systems under non-standard conditions are a property worthy of attention. Having established the relationship between potential and free energy change in this section, the previously discussed relation between free energy change and reaction mixture composition can be used for this purpose. Delta letter 1D43A equals delta letter 1D43A plus, letter 1D445, letter 1D447 ln, letter 1D444. Notice the reaction quotient, Q, appears in this equation, making the free energy change dependent upon the composition of the reaction mixture. Substituting the equation relating free energy change to cell potential yields the Nernst equation. minus letter 1d45b, letter 1d439, letter 1d438 cell equals minus letter 1d45b, letter 1d439, letter 1d438 cell, plus letter 1d445, letter 1d447 ln, letter 1d444. Letter 1d438 cell equals letter 1d438 cell minus letter 1d445, letter 1d447, letter 1d45b, letter 1d439 ln, letter 1d444. This equation describes how the potential of a redox system, such as a galvanic cell, varies from its standard state value, specifically showing it to be a function of the number of electrons transferred, N, the temperature, T, and the reaction mixture composition as reflected in Q. A convenient form of the Nernst equation for most work is one in which values for the fundamental constants, R and F, and standard temperature, 298 K, along with a factor converting from natural to base 10 logarithms, have been included. Letter 1d438 cell equals letter 1d438 cell minus 0. 0592 v letter 1d45b log, letter 1d444. Example 17. 7. Predicting redox spontaneity under non-standard conditions. Use the Nernst equation to predict the spontaneity of the redox reaction shown below. Co, letter 1d460, plus Phe2 plus, letter 1d440, letter 1d45e, 1. 94, letter 1d440. Co 2 plus, letter 1d440, letter 1d45e, 015, letter 1d440, plus Phi, letter 1d460. Solution. Collecting information from Appendix L and the problem. Anode oxidation. Cathode reduction. Co letter 1d460. Co 2 plus, letter 1d440, letter 1d45e, plus 2e minus Phi2 plus, letter 1d440, letter 1d45e, plus 2e minus Phi, letter 1d460, letter 1d438 cell equals letter 1d438 cathode minus letter 1d438 anode equals letter 1d438 co 2 plus slash co letter 1d438 Phi2 plus slash Phi minus 0. 447 V minus 0. 28 V equals minus 0. 28 V minus 0. 447 V minus 0. 17 V. Notice the negative value of the standard cell potential indicates the process is not spontaneous under standard conditions. Substitution of the Nernst equation terms for the non-standard conditions yields letter 1d444, letter 1d438 cell, letter 1d438 cell, letter 1d438 cell equals co 2 plus Phi2 plus equals 0. 15 M1. 94 letter 1d440 equals 0. 77 letter 1d438 cell minus 0. 592 v letter 1d45b log letter 1d444 minus 0. 17 v minus 0. 592 v to log 0. 77 minus 0. 17 v plus 0. 33 v equals minus 0. 14 v. The cell potential remains negative slightly under the specified conditions, and so the reaction remains non-spontaneous. Check your learning. For the cell schematic below, identify values for N and Q and calculate the cell potential, SL. Al 3 plus, letter 1d440, letter 1d45e, 0. 15 letter 1d440. Q 2 plus, letter 1d440, letter 1d45e, 0. 25 letter 1d440. Q, letter 1d460. Answer N equals 6. Q equals 1440, SL equals plus 1, 97 V spontaneous. A concentration cell is constructed by connecting two nearly identical half cells, each based on the same half reaction, and using the same electrode, varying only in the concentration of one redox species. The potential of a concentration cell, therefore, is determined only by the difference in concentration of the chosen redox species. The example problem below illustrates the use of the Nernst equation in calculations involving concentration cells. Example 17. 8. Concentration cells. What is the cell potential of the concentration cell described by Zn letter 1d460, Zn2 plus, letter 1d44e, letter 1d45e, 0. 10 letter 1d440, Zn2 plus, letter 1d44e, letter 1d45e, 0. 50 letter 1d440, Zn letter 1d460. Solution. From the information given, anode, cathode. Zn letter 1d460, Zn2 plus, letter 1d44e, letter 1d45e, 0. 10 letter 1d440, plus 2e minus Zn2 plus, letter 1d44e, letter 1d45e, 0. 50 letter 1d440, plus 2e minus Zn, letter 1d460, letter 1d438 anode, letter 1d438 cathode equals minus 0. 7618V minus 0. 7618V overall. Zn2 plus, letter 1d44e, letter 1d45e, 0. 50 letter 1d440, Zn2 plus, letter 1d44e, letter 1d45e, 0. 10 letter 1d440, letter 1d438 cell equals 0. 0V. Substituting into the Nernst equation. Letter 1d438 cell equals 0. 0V minus 0. 592V to log 0. 100. 50 equals plus 0. 21V. The positive value for cell potential indicates the overall cell reaction, see above, is spontaneous. This spontaneous reaction is one in which the zinc ion concentration in the cathode falls. It is reduced to elemental zinc. While that in the anode rises, it is produced by oxidation of the zinc anode. A greater driving force for zinc reduction is present in the cathode, where the zinc Roman II ion concentration is greater ecathode enode. Check your learning. The concentration cell above was allowed to operate until the cell reaction reached equilibrium. What are the cell potential and the concentrations of zinc Roman II in each half cell for the cell now? Answer. SL equals 00V. Zn2 plus cathode equals Zn2 plus anode equals 0. 30M. Learning objectives. By the end of this section, you will be able to describe the electrochemistry associated with several common batteries. Distinguish the operation of a fuel cell from that of a battery. There are many technological products associated with the past 2 centuries of electrochemistry research, none more immediately obvious than the battery. A battery is a galvanic cell that has been specially designed and constructed in a way that best suits its intended use, a source of electrical power for specific applications. Among the first successful batteries was the Daniell cell, which relied on the spontaneous oxidation of zinc by copper, Roman II ions, figure 17. 8. Zn, letter 1d460, plus Cu2 plus, letter 1d44e, letter 1d45e, Zn2 plus, letter 1d44e, letter 1d45e, plus Cu, letter 1d460. This figure contains a patent drawing for an electrochemical cell on the left labeled element Daniell, and a diagram of an electrochemical cell on the right. In the diagram, 2 beakers are shown. Each is just over half full. The beaker on the left contains a blue solution. The beaker on the right contains a colorless solution. A glass tube in the shape of an inverted U connects the 2 beakers at the center of the diagram. The tube contents are colorless. The ends of the tubes are beneath the surface of the solutions in the beakers, and a small gray plug is present at each end of the tube. The plug in the left beaker is labeled porous plug. Each beaker shows a metal strip partially submerged in the liquid. The beaker on the left has a silver strip that is labeled Zn anode at the top. The beaker on the right has an orange-brown strip that is labeled Cu cathode at the top. A wire extends up and toward the center from the top of each of these strips before stopping. The end of the left wire points up to a negative sign. The end of the right wire points up to a positive sign, An arrow points toward the left wire, which is labeled flow of E superscript negative. A curved arrow extends from the ZN strip into the surrounding solution. The tip of this arrow is labeled ZN superscript 2 plus. A curved arrow extends from the salt bridge into the beaker on the left into the blue solution. The tip of this arrow is labeled SO subscript 4 superscript 2 negative. A curved arrow extends from the solution in the beaker on the right to the CU strip. The base of this arrow is labeled CU superscript 2 plus. A curved arrow extends from the colorless solution to salt bridge in the beaker on the right. The base of this arrow is labeled SO subscript 4 superscript 2 negative. Just right of the center of the salt bridge on the tube, an arrow is placed on the salt bridge that points down and to the right. The base of this arrow is labeled ZN superscript 2 plus. Just above this region of the tube appears the label flow of cations. Just left of the center of the salt bridge on the tube, an arrow is placed on the salt bridge that points down and to the left. The base of this arrow is labeled SO subscript 4 superscript 2 negative. Just above this region of the tube appears the label flow of anions. Figure 17. 8 illustration of a Daniell cell taken from a 1904 journal publication. Left, along with a simplified illustration depicting the electrochemistry of the cell. Right. The 1904 design used a porous clay pot to both contain one of the half cell's content and to serve as a salt bridge to the other half cell. Modern batteries exist in a multitude of forms to accommodate various applications, from tiny button batteries that provide the modest power needs of a wristwatch to the very large batteries used to supply backup energy to municipal power grids. Some batteries are designed for single-use applications and cannot be recharged, primary cells, while others are based on conveniently reversible cell reactions that allow recharging by an external power source, secondary cells. This section will provide a summary of the basic electrochemical aspects of several batteries familiar to most consumers, and will introduce a related electrochemical device called a fuel cell that can offer improved performance in certain applications. Link to learning. Visit this site to learn more about batteries. Single-use batteries. A common primary battery is the dry cell, which uses a zinc can as both container and anode, terminal, and a graphite rod as the cathode, plus terminal. The ZN can is filled with an electrolyte paste containing manganese, Roman 4, oxide, zinc, Roman 2, chloride, ammonium chloride, and water. A graphite rod is immersed in the electrolyte paste to complete the cell. The spontaneous cell reaction involves the oxidation of zinc. Anode reaction. Zn, letter 1d460, Zn2 plus, letter 1d44e, letter 1d45e, plus 2e minus. And the reduction of manganese, Roman 4. Reduction reaction. 2MnO2, letter 1d460, plus 2NH4Cl, letter 1d44e, letter 1d45e, plus 2E minus Mn2O3, letter 1d460, plus 2NH3, letter 1d44e, letter 1d45e, plus H2O, letter 1d459, plus 2Cl minus, which together yield the cell reaction. Cell reaction. 2MnO2, letter 1d460, plus 2NH4Cl, letter 1d44e, letter 1d45e, plus Zn, letter 1d460, Zn2 plus letter 1d44e, letter 1d45e, plus Mn2O3, letter 1d460, plus 2NH3, letter 1d44e, letter 1d45e, plus H2O, letter 1d459, plus 2Cl minus letter 1d438 cell tilde 1. 5V. The voltage cell potential of a dry cell is approximately 1. 5V dry cells are available in various sizes, e.g. D, C, AA, AAA. All sizes of dry cells comprise the same components, and so they exhibit the same voltage, but larger cells contain greater amounts of the redox reactants and therefore are capable of transferring correspondingly greater amounts of charge. Like other galvanic cells, dry cells may be connected in series to yield batteries with greater voltage outputs, if needed. A diagram of a cross-section of a dry cell battery is shown. The overall shape of the cell is cylindrical. The lateral surface of the cylinder, indicated as a thin red line, is labeled zinc-can electrode. Just beneath this is a slightly thicker dark gray surface that covers the lateral surface, top and bottom of the battery, which is labeled porous separator. Inside is a purple region with many evenly spaced small darker purple dots, labeled paste of MnO subscript 2, NH subscript 4Cl, ZnCl subscript 2, water cathode. A dark gray rod, labeled carbon rod electrode, extends from the top of the battery, leaving a gap of less than 1/5 the height of the battery below the rod to the bottom of the cylinder. A thin gray line segment at the very bottom of the cylinder is labeled metal bottom cover negative. The very top of the cylinder has a thin gray surface that curves upward at the center over the top of the carbon electrode at the center of the cylinder. This upper surface is labeled metal top cover positive. A thin dark gray line just below this surface is labeled insulator. Below this, above the purple region, and outside of the carbon electrode at the center, is an orange region that is labeled seal. Figure 17. 9. A schematic diagram shows a typical dry cell, linked to learning. Visit this site to learn more about zinc-carbon batteries. Alkaline batteries, Figure 17. 10 were developed in the 1950s to improve on the performance of the dry cell, and they were designed around the same redox couples. As their name suggests, these types of batteries use alkaline electrolytes, often potassium hydroxide. The reactions are anode, Zn letter 1d460, plus 2O minus, letter 1d44, letter 1d45e, ZnO letter 1d460 plus H2O, letter 1d459, plus 2E minus cathode. 2MnO2, letter 1d460, plus H2O, letter 1d459, plus 2E minus Mn2O3, letter 1d460, plus 2O minus, letter 1d44e, letter 1d45e cell. Zn, letter 1d460, plus 2MnO2, letter 1d460, ZnO, letter 1d460, plus Mn2O3, letter 1d460, letter 1d438 cell equals plus 1. 43V. An alkaline battery can deliver about 3 to 5 times the energy of a zinc-carbon dry cell of similar size. Alkaline batteries are prone to leaking potassium hydroxide, so they should be removed from devices for long-term storage. While some alkaline batteries are rechargeable, most are not. Attempts to recharge an alkaline battery that is not rechargeable often leads to rupture of the battery and leakage of the potassium hydroxide electrolyte. A diagram of a cross-section of an alkaline battery is shown. The overall shape of the cell is cylindrical. The lateral surface of the cylinder, indicated as a thin red line, is labeled outer casing. Just beneath this is a thin, light gray surface that covers the lateral surface and top of the battery. Inside is a blue region with many evenly spaced small darker dots, labeled MnO subscript 2, cathode. A thin dark gray layer is just inside, which is labeled ion conducting separator. A purple region with many evenly spaced small darker dots fills the center of the battery and is labeled zinc anode. The very top of the battery has a thin gray curved surface over the central purple region. The curved surface above is labeled positive connection plus. At the base of the battery, an orange structure, labeled protective cap, is located beneath the purple and blue central regions. This structure holds a gray structure that looks like a nail with its head at the bottom and pointed end extending upward into the center of the battery. This nail-like structure is labeled current pickup. At the very bottom of the battery is a thin gray surface that is held by the protective cap. This surface is labeled negative terminal negative. Figure 17. 10 alkaline batteries were designed as improved replacements for zinc-carbon dry cell batteries. Link to learning. Visit this site to learn more about alkaline batteries. Rechargeable secondary batteries. Nickel-cadmium or NiCd batteries figure 17. 11 consist of a nickel-plated cathode, cadmium-plated anode, and a potassium hydroxide electrode. The positive and negative plates, which are prevented from shorting by the separator, are rolled together and put into the case. This is a jelly-rolled design and allows the NiCd cell to deliver much more current than a similar-sized alkaline battery. The reactions are anode CD letter 1D460 plus 2O minus letter 1D44 letter 1D45 ECD O2 letter 1D460 plus 2E minus cathode. NiO2 letter 1D460 plus 2H2 letter 1D459 plus 2E minus NiO2 letter 1D460 plus 2O minus letter 1D44 letter 1D45E cell. CD letter 1D460 plus NiO2 letter 1D460 plus 2H2 letter 1D459 CD O2 letter 1D460 plus NiO2 letter 1D460 letter 1D438 cell tilde 1. 2V. When properly treated, a NiCd battery can be recharged about 1,000 times. Cadmium is a toxic heavy metal, so NiCd batteries should never be ruptured or incinerated, and they should be disposed of in accordance with relevant toxic waste guidelines. A diagram is shown of a cross-section of a nickel-cadmium battery. This battery is in a cylindrical shape. An outer red layer is labeled case. Just inside this layer is a thin, dark gray layer which is labeled at the bottom of the cylinder as negative electrode collector. A silver rod extends upward through the center of the battery, which is surrounded by alternating layers, shown as vertical repeating bands of yellow, purple, yellow, and blue. A slightly darker gray narrow band extends across the top of these alternating bands, which is labeled positive electrode collector. A thin light gray band appears at the very bottom of the cylinder, which is labeled metal bottom cover negative. A small gray and white striped rectangular structure is present at the top of the central silver cylinder, which is labeled safety valve. Above this is an orange layer that curves upward over the safety valve, which is labeled insulation ring. Above this is a thin light gray layer that projects upward slightly at the center, which is labeled metal top cover plus. A light gray arrow points to a rectangle to the right that illustrates the layers at the center of the battery under magnification. From the central silver rod, the layers shown repeat the alternating pattern yellow, blue, yellow, and purple 3 times, with a final yellow layer covering the last purple layer. The outermost purple layer is labeled negative electrode. The yellow layer beneath it is labeled separator. The blue layer just inside is labeled positive electrode. Figure 17. 11 NiCd batteries use a jelly roll design that significantly increases the amount of current the battery can deliver as compared to a similar-sized alkaline battery. Link to learning. Visit this site for more information about nickel-cadmium rechargeable batteries. Lithium-ion batteries, figure 17. 12, are among the most popular rechargeable batteries and are used in many portable electronic devices. The reactions are cathode, Li1 minus letter 1D465 Co O2 plus letter 1D465 Li plus plus letter 1D465 E minus Li Co O2 anode. Letter 1D465 Li C6 letter 1D465 Li plus plus letter 1D465 E minus plus letter 1D465 C6 cell. Li1 minus letter 1D465 Co O2 plus letter 1D465 Li C6 Li Co O2 plus letter 1D465 C6 letter 1D438 cell tilde 3. 7V. The variable stoichiometry of the cell reaction leads to variation in cell voltages, but for typical conditions, X is usually no more than 0.5, and the cell voltage is approximately 37V. Lithium batteries are popular because they can provide a large amount current, are lighter than comparable batteries of other types, produce a nearly constant voltage as they discharge, and only slowly lose their charge when stored. This figure shows a model of the flow of charge in a lithium-ion battery. At the left, an approximately cubic structure formed by alternating red, gray, and purple spheres is labeled below as positive electrode. The purple spheres are identified by the label lithium. The gray spheres are identified by the label metal. The red spheres are identified by the label oxygen. Above this structure is the label charge, followed by a right-pointing green arrow. At the right is a figure with layers of black interconnected spheres, with purple spheres located in gaps between the layers. The black layers are labeled graphite layers. Below the purple and black structure is the label negative electrode. Above is the label discharge, which is preceded by a blue arrow which points left. At the center of the diagram between the two structures are 6 purple spheres which are each labeled with a plus symbol. 3 curved green arrows extend from the red, purple, and gray structure to each of the 3 closest purple plus labeled spheres. Green curved arrows extend from the right side of the upper and lower of these 3 purple plus labeled spheres to the black and purple layered structure. 3 blue arrows extend from the purple and black layered structure to the remaining 3 purple plus labeled spheres at the center of the diagram. The base of each arrow has a circle formed by a dashed curved line in the layered structure. The lowest of the 3 purple plus marked spheres reached by the blue arrows has a second blue arrow extending from its left side, which points to a purple sphere in the purple, green, and gray structure. Figure 17:12 in a lithium-ion battery, charge flows as the lithium ions are transferred between the anode and cathode. Link to learning. Visit this site for more information about lithium-ion batteries. The lead-acid battery, Figure 1713, is the type of secondary battery commonly used in automobiles. It is inexpensive and capable of producing the high current required by automobile starter motors. The reactions for a lead-acid battery are anode, Pb, letter 1d460, plus HSO4 minus letter 1d44e, letter 1d45e, Pb, SO4, letter 1d460, plus H plus, letter 1d44e, letter 1d45e, plus 2e minus cathode, PbO2, letter 1d460, plus HSO4 minus letter 1d44e, letter 1d45e, plus 3H plus, letter 1d44e, letter 1d45e, plus 2e minus Pb, SO4, letter 1d460, plus 2H2, letter 1d459 cell, Pb, letter 1d460, plus PbO2, letter 1d460, plus 2H2SO4, letter 1d44e, letter 1d45e2, Pb, SO4, letter 1d460, plus 2H2, letter 1d459, letter 1d438 cell tilde 2V. Each cell produces 2V, so 6 cells are connected in series to produce a 12V car battery. Lead-acid batteries are heavy and contain a caustic liquid electrolyte, H2SO4, AC, but are often still the battery of choice because of their high current density. Since these batteries contain a significant amount of lead, they must always be disposed of properly. A diagram of a lead-acid battery is shown. A black outer casing, which is labeled protective casing, is in the form of a rectangular prism. Gray cylindrical projections extend upward from the upper surface of the battery in the back left and back right corners. At the back right corner, the projection is labeled positive terminal. At the back right corner, the projection is labeled negative terminal. The bottom layer of the battery diagram is a dark green color, which is labeled dilute H subscript 2 SO subscript 4. A blue outer covering extends upward from this region near the top of the battery. Inside, alternating gray and white vertical sheets are packed together in repeating units within the battery. The battery has the sides cut away to show three of these repeating units, which are separated by black vertical dividers, which are labeled as cell dividers. The gray layers in the repeating units are labeled negative electrode, lead. The white layers are labeled positive electrode, lead dioxide. Figure 17. 13. The lead acid battery in your automobile consists of 6 cells connected in series to give 12V. Link to learning. Visit this site for more information about lead acid batteries. Fuel cells. A fuel cell is a galvanic cell that uses traditional combustive fuels, most often hydrogen or methane, that are continuously fed into the cell along with an oxidant. An alternative but not very popular name for a fuel cell is a flow battery. Within the cell, fuel and oxidant undergo the same redox chemistry as when they are combusted, but via a catalyzed electrochemical that is significantly more efficient. For example, a typical hydrogen fuel cell uses graphite electrodes embedded with platinum-based catalysts to accelerate the two half-cell reactions. A diagram is shown of a hydrogen fuel cell. At the center is a vertical rectangle which is shaded dark gray and labeled electrolyte. This region has two labels for H superscript plus in it. To the right and left are narrow vertical rectangles shaded light gray. The one to the right is labeled cathode, and the one to the left is labeled anode. To the left of the leftmost light gray region is a white region shaped like a closed left bracket. A yellow arrow points into the white region with the label to show fuel in. In the middle of the white area are two yellow arrows pointing toward the gray shading labeled H subscript 2. At the bottom of the white region is a yellow arrow pointing out that is labeled excess fuel. On the right side is another white region that makes a right closed bracket shape. There are two arrows with the label air in, and H subscript 2O in the upper left side of this area pointing in. One arrow is light blue and one is dark blue. In the middle to the white area is a light blue arrow pointing toward the gray shading. The arrow is labeled O subscript 2. Below that are two dark blue arrows pointing out from the gray shading to the white area labeled H subscript 2O. At the bottom of the white region are the light blue arrow for O subscript 2 and the dark blue arrow for H subscript 2, O pointing out. This is labeled unused gases out. Black line segments extend upward from the light gray shaded regions. These line segments are connected by a horizontal segment that has a curly shape in a circle at the center. This shape is labeled electric current. In the left light gray shaded region above the yellow arrows is a red arrow pointing up, the label E superscript minus above it, and then another red arrow. The black line segment above this area also has the label E superscript minus. Where the line turns right to connect to the electric current shape is a right-facing red arrow. On the other side of the shape, where the line turns downward to connect to the other light gray shaded region, is a red downward-facing arrow. Below that arrow in the light gray region is the label E superscript minus, followed by a red down arrow, followed by another E superscript minus label that stops before the light blue arrow pointing into the shaded area. Figure 17. 14. In this hydrogen fuel cell, oxygen from the air reacts with hydrogen producing water and electricity. Anode, 2H2, letter 1D454, 4H+, letter 1D44E, letter 1D45E, plus 4E minus cathode. O2, letter 1D454, plus 4H+, letter 1D44E, letter 1D45E, plus 4E minus 2H2O, letter 1D454 cell. 2H2, letter 1D454 plus O2, letter 1D454 2H2O, letter 1D454, letter 1D438 cell tilde 1. 2V. These types of fuel cells generally produce voltages of approximately 1. 2V compared to an internal combustion engine. The energy efficiency of a fuel cell using the same redox reaction is typically more than double % for an engine versus tilde 50% 75% for a fuel cell. Hydrogen fuel cells are commonly used on extended space missions, and prototypes for personal vehicles have been developed, though the technology remains relatively immature. Link to learning. Check out this link to learn more about fuel cells. Learning objectives. By the end of this section, you will be able to define corrosion. List some of the methods used to prevent or slow corrosion. Corrosion is usually defined as the degradation of metals by a naturally occurring electrochemical process. The formation of rust on iron, tarnish on silver, and the blue-green patina that develops on copper are all examples of corrosion. The total cost of corrosion remediation in the United States is significant, with estimates in excess of $500 billion a year. Chemistry in everyday life. Statue of Liberty. Changing colors. The Statue of Liberty is a landmark every American recognizes. The Statue of Liberty is easily identified by its height, stance, and unique blue-green color. Figure 17. 15. When this statue was first delivered from France, its appearance was not green. It was brown, the color of its copper skin. So how did the Statue of Liberty change colors? The change in appearance was a direct result of corrosion. The copper that is the primary component of the statue slowly underwent oxidation from the air. The oxidation-reduction reactions of copper metal in the environment occur in several steps. Copper metal is oxidized to copper I oxide Cu2O, which is red, and then to copper Roman 2 oxide, which is black 2 Cu letter 1 D460, plus 12O2 letter 1 D454 Cu2O letter 1 D460, red Cu2O letter 1 D460, plus 12O2 letter 1 D4542 Cu2O letter 1 D460, black coal, which was often high in sulfur, was burned extensively in the early part of the last century. As a result, atmospheric sulfur trioxide, carbon dioxide, and water all reacted with the Cu-O2 Cu-O letter 1D460, plus Co2 letter 1D454, plus H2O letter 1D459 Cu-3O2 letter 1D460, green 3 Cu-O letter 1D460, plus 2 Co2 letter 1D454, plus H2O letter 1D459 Cu2 Co3 2O2 letter 1D460, blue 4 Cu-O letter 1D460, plus O3 letter 1D454 plus 3 H2O letter 1D459 Cu4 So4 O6 letter 1D460, green. These three compounds are responsible for the characteristic blue-green patina seen on the Statue of Liberty and other outdoor copper structures. Fortunately, formation of patina creates a protective layer on the copper surface, preventing further corrosion of the underlying copper. The formation of the protective layer is called passivation, a phenomenon discussed further in another chapter of this text. This figure contains two photos of the Statue of Liberty. Photo A appears to be an antique photo which shows the original brown color of the copper-covered statue. Photo B shows the blue-green appearance of the statue today. In both photos, the statue is shown atop a building, with a body of water in the background. Figure 1715 A. The Statue of Liberty is covered with a copper skin and was originally brown, as shown in this painting. B. Exposure to the elements has resulted in the formation of the blue-green patina seen today. Perhaps the most familiar example of corrosion is the formation of rust on iron. Iron will rust when it is exposed to oxygen and water. Rust formation involves the creation of a galvanic cell at an iron surface, as illustrated in Figure 17. The relevant redox reactions are described by the following equations: anode, cathode, overall. Phi letter 1D460, Phi 2 plus, letter 1D44, letter 1D45E, plus 2E minus O2, letter 1D454, plus 4H plus, letter 1D44, letter 1D45E, plus 4E minus 2H2, letter 1D4592 Phi, letter 1D460 plus O2, letter 1D454 plus 4H plus, letter 1D44, letter 1D45E2, Phi 2 plus, letter 1D44, letter 1D45E, plus 2H2. O letter 1D459, letter 1D438 Phi 2 plus slash Phi letter 1D438, O2 slash OTA letter 1D438 cell equals minus 0. 44V plus 1. 23V plus 1. 67V further reaction of the iron Roman 2 product in humid air results in the production of an iron Roman 3 oxide hydrate known as rust. 4Fe2 plus letter 1D44 letter 1D45E plus O2 letter 1D454 plus 4 plus 2 letter 1D465H2 letter 1D4592 Fe2O3 letter 1D465H2 letter 1D460 plus 8H plus letter 1D44E letter 1D45E. The stoichiometry of the hydrate varies, as indicated by the use of X in the compound formula. Unlike the patina on copper, the formation of rust does not create a protective layer, and so corrosion of the iron continues as the rust flakes off and exposes fresh iron to the atmosphere. A gray rectangle labeled iron is shown with thin purple layers, labeled paint layer, at its upper and lower surfaces. A gap in the upper purple layer at the upper left of the diagram is labeled cathodic site. A blue droplet labeled water is positioned on top of the gap. A curved arrow extends from a space above the droplet to the surface of the gray region and into the water droplet. The base of the arrow is labeled O subscript 2, and the tip of the arrow is labeled H subscript 2 O. A gap to the right, and on the bottom side of the gray region shows that some of the gray region is gone from the region beneath the purple layer. A water droplet covers this gap and extends into the open space in the gray rectangle. The label Fe superscript 2 positive is at the center of the droplet. A curved arrow points from the edge of the gray area below to the label. A second curved arrow extends from the Fe superscript 2 positive arrow to a rust-brown chunk on the lower surface of the purple layer at the edge of the water droplet. A curved arrow extends from O subscript 2 outside the droplet into the droplet to the rust-brown chunk. The gray region at the lower right portion of the diagram is labeled anodic site. An arrow extends from the anodic site toward the cathodic site, which is labeled E superscript negative. Figure 17. 16 corrosion can occur when a painted iron or steel surface is exposed to the environment by a scratch through the paint. A galvanic cell results that may be approximated by the simplified cell schematic Fe(S), Fe2 plus AC02 AC H2O L Fe(S). One way to keep iron from corroding is to keep it painted. The layer of paint prevents the water and oxygen necessary for rust formation from coming into contact with the iron. As long as the paint remains intact, the iron is protected from corrosion. Other strategies include alloying the iron with other metals. For example, stainless steel is an alloy of iron containing a small amount of chromium. The chromium tends to collect near the surface, where it corrodes and forms a passivating and oxide layer that protects the iron. Iron and other metals may also be protected from corrosion by galvanization, a process in which the metal to be protected is coated with a layer of a more readily oxidized metal, usually zinc. When the zinc layer is intact, it prevents air from contacting the underlying iron and thus prevents corrosion. If the zinc layer is breached by either corrosion or mechanical abrasion, the iron may still be protected from corrosion by a cathodic protection process, which is described in the next paragraph. Another important way to protect metal is to make it the cathode in a galvanic cell. This is cathodic protection and can be used for metals other than just iron. For example, the rusting of underground iron storage tanks and pipes can be prevented or greatly reduced by connecting them to a more active metal such as zinc or magnesium. Figure 17. 17. This is also used to protect the metal parts in water heaters. The more active metals' lower reduction potential are called sacrificial anodes because as they get used up as they corrode, oxidize at the anode. The metal being protected serves as the cathode for the reduction of oxygen in air, and so it simply serves to conduct, not react with, the electrons being transferred. When the anodes are properly monitored and periodically replaced, the useful lifetime of the iron storage tank can be greatly extended. A diagram is shown of an underground storage tank system. Underground is a metal tank-like structure, labeled sacrificial anode, which is vertically oriented. Mg is on the tank, followed by a right arrow, followed by Mg superscript 2+. A black line extends upward from the center of the tank, but stays underground. A horizontal black line segment continues right underground. 2, E superscript minus is followed by an arrow that points right below the line segment. A vertical black line segment leads downward to a horizontal gray tank which is labeled object to be protected, cathode. 2, E subscript minus is on the tank with an arrow pointing from it to the ground below the tank. Below that arrow is 2H superscript plus plus O subscript 2, arrow 2H subscript 2O, figure 17. 17. Cathodic protection is a useful approach to electrochemically preventing corrosion of underground storage tanks. Learning objectives. By the end of this section, you will be able to describe the process of electrolysis, compare the operation of electrolytic cells with that of galvanic cells, perform stoichiometric calculations for electrolytic processes, electrochemical cells, in which spontaneous redox reactions take place. Galvanic cells have been the topic of discussion so far in this chapter. In these cells, electrical work is done by a redox system on its surroundings, as electrons produced by the redox reaction are transferred through an external circuit. This final section of the chapter will address an alternative scenario in which an external circuit does work on a redox system by imposing a voltage sufficient to drive an otherwise non-spontaneous reaction, a process known as electrolysis. A familiar example of electrolysis is recharging a battery, which involves use of an external power source to drive the spontaneous discharge cell reaction in the reverse direction, restoring to some extent the composition of the half cells and the voltage of the battery. Perhaps less familiar is the use of electrolysis in the refinement of metallic ores, the manufacture of commodity chemicals, and the electroplating of metallic coatings on various products, e.g., jewelry, utensils, auto parts. To illustrate the essential concepts of electrolysis, a few specific processes will be considered. The electrolysis of molten sodium chloride, metallic sodium, Na, and chlorine gas, Cl2, are used in numerous applications, and their industrial production relies on the large-scale electrolysis of molten sodium chloride, NaCl. The industrial process typically uses a down cell similar to the simplified illustration shown in Figure 17. 18. The reactions associated with this process are anode, 2Cl-, letter 1D459Cl2, letter 1D454 plus 2E- cathode, Na plus, letter 1D459 plus E- Na, letter 1D459 cell, 2 Na plus, letter 1D459 plus 2Cl-, letter 1D459 2 Na, letter 1D459 plus Cl2, letter 1D454. The cell potential for the above process is negative, indicating the reaction as written. Decomposition of liquid NaCl is not spontaneous. To force this reaction, a positive potential of magnitude greater than the negative cell potential must be applied to the cell. This diagram shows a tank containing a light blue liquid, labeled molten and a Cl. A vertical dark gray divider with small, evenly distributed dark dots, labeled porous screen, is located at the center of the tank, dividing it into two halves. Dark gray bars are positioned at the center of each of the halves of the tank. The bar on the left, which is labeled anode, has green bubbles originating from it. The bar on the right, which is labeled cathode, has light gray bubbles originating from it. An arrow points left from the center of the tank toward the anode, which is labeled Cl superscript negative. An arrow points right from the center of the tank toward the cathode, which is labeled N a superscript plus. A line extends from the tops of the anode and cathode to a rectangle centrally placed above the tank, which is labeled voltage source. An arrow extends upward above the anode to the left of the line, which is labeled E superscript negative. A plus symbol is located to the left of the voltage source, and a negative sign is located to its right. An arrow points downward along the line segment leading to the cathode. This arrow is labeled E superscript negative. The left side of below the diagram is the label 2Cl superscript negative right pointing arrow Cl subscript 2, G, plus 2 E superscript negative. At the right below the diagram is the label 2 and a superscript plus 2 E superscript negative right pointing arrow 2 and a L. Figure 17. 18 cells of this sort, a cell for the electrolysis of molten sodium chloride, are used in the Downs process for production of sodium and chlorine, and they typically use iron cathodes and carbon anodes. The electrolysis of water may be electrolytically decomposed in a cell similar to the one illustrated in Figure 17. 19. To improve electrical conductivity without introducing a different redox species, the hydrogen ion concentration of the water is typically increased by addition of a strong acid. The redox processes associated with this cell are anode 2H2O, letter 1D459O2, letter 1D454, plus 4H plus, letter 1D44E, letter 1D45E, plus 4E minus cathode, 2H plus, letter 1D44E, letter 1D45E, plus 2E minus H2, letter 1D454, letter 1D438 anode, letter 1D438 cathode equals plus 1. 229V0V cell. 2H2O, letter 1D4592H2, letter 1D454, plus O2, letter 1D454, letter 1D438 cell equals minus 1. 229V again. The cell potential as written is negative, indicating a non-spontaneous cell reaction that must be driven by imposing a cell voltage greater than plus 1. 229V. Keep in mind that standard electrode potentials are used to inform thermodynamic predictions here, though the cell is not operating under standard state conditions. Therefore, at best, calculated cell potentials should be considered ballpark estimates. This figure shows an apparatus used for electrolysis. A central chamber with an open top has a vertical column extending below that is nearly full of a clear, colorless liquid, which is labeled H subscript 2 O plus H subscript 2 SO subscript 4. A horizontal tube in the apparatus connects the central region to vertical columns to the left and right, each of which has a valve or stopcock at the top and a stoppered bottom. On the left, the stopper at the bottom has a small brown square connected just above it in the liquid. The square is labeled anode plus. A black wire extends from the stopper at the left to a rectangle which is labeled voltage source onto the stopper at the right. The left side of the rectangle is labeled with a plus symbol, and the right side is labeled with a negative sign. The stopper on the right also has a brown square connected to it, which is in the liquid in the apparatus. This square is labeled cathode negative. The level of the solution on the left arm or tube of the apparatus is significantly higher than the level of the right arm. Bubbles are present near the surface of the liquid on each side of the apparatus, with the bubbles labeled as O subscript 2 G on the left and H subscript 2 G on the right. Figure 17. 19. The electrolysis of water produces stoichiometric amounts of oxygen gas at the anode and hydrogen at the cathode. The electrolysis of aqueous sodium chloride when aqueous solutions of ionic compounds are electrolyzed. The anode and cathode half reactions may involve the electrolysis of either water species, H2O, H plus, O or solute species, the cations and anions of the compound. As an example, the electrolysis of aqueous sodium chloride could involve either of these two anode reactions. I2Cl-, letter 1D44E, letter 1D45E Cl2, letter 1D454, plus 2E-, Roman 22H2, letter 1 D45902, letter 1 D454 plus, 4H plus letter 1 D44, letter 1 D45E, plus 4E minus letter 1 D438, anode letter 1 D438, anode plus 1. 35,827, V plus 1. 229 V, the standard electrode reduction. Potentials of these two half reactions indicate water may be oxidized at a less negative, more positive potential. 1. 229 V, than chloride ion, 1358 V. Thermodynamics thus predicts that water would be more readily oxidized, though in practice it is observed that both water and chloride ion are oxidized under typical conditions, producing a mixture of oxygen and chlorine gas. Turning attention to the cathode, the possibilities for reduction are Roman 3,2H plus, letter 1D44, letter 1D45E, plus 2E minus H2, letter 1D454, Roman 4,2H2, O letter 1D459, plus 2E minus H2, letter 1D454, plus 2O minus letter 1D44, letter 1D45E, V na plus, letter 1D44, letter 1D45E plus, E minus na letter 1D460, letter 1D438, cathode, letter 1D438, cathode, letter 1D438, cathode 0, V minus 0, 8277, V minus 2. 71 V. Comparison of these standard half-reaction potentials suggests the reduction of hydrogen ion is thermodynamically favored. However, in a neutral aqueous sodium chloride solution, the concentration of hydrogen ion is far below the standard state value of 1 m, approximately 10·7 m, and so the observed cathode reaction is actually reduction of water. The net cell reaction in this case is then cell 2H2, letter 1D459, plus 2Cl minus, letter 1D44, letter 1D45EH2, letter 1D454, plus Cl2, letter 1D454, plus 2O minus, letter 1D44, letter 1D45E, letter 1D438 cell equals minus 2. 186 V. This electrolysis reaction is part of the chloralkali process used by industry to produce chlorine and sodium hydroxide, Li. Chemistry in everyday life. Electroplating. An important use for electrolytic cells is in electroplating. Electroplating results in a thin coating of one metal on top of a conducting surface. Reasons for electroplating include making the object more corrosion resistant, strengthening the surface, producing a more attractive finish, or for purifying metal. The metals commonly used in electroplating include cadmium, chromium, copper, gold, nickel, silver, and tin. Common consumer products include silver-plated or gold-plated tableware, chrome-plated automobile parts, and jewelry. The silver plating of eating utensils is used here to illustrate the process. Figure 17.20. This figure contains a diagram of an electrochemical cell. One beaker is shown that is just over half full. The beaker contains a clear, colorless solution that is labeled a GNO subscript 3. A Q. A silver strip is mostly submerged in the liquid on the left. This strip is labeled silver anode. The top of the strip is labeled with a red plus symbol. An arrow points right from the surface of the metal strip into the solution to the label, a G superscript plus, to the right. A spoon is similarly suspended in the solution and is labeled spoon cathode. It is labeled with a black negative sign on the tip of the spoon's handle above the surface of the liquid. An arrow extends from the label, a G superscript plus, to the spoon on the right. A wire extends from the top of the spoon and the strip to a rectangle labeled voltage source. An arrow points upward from silver strip which is labeled E superscript negative. Similarly, an arrow points down at the right to the surface of the spoon which is also labeled E superscript negative. A plus sign is shown just outside the voltage source to the left, and a negative is shown to its right. Figure 17.20. This schematic shows an electrolytic cell for silver plating eating utensils. In the figure, the anode consists of a silver electrode, shown on the left. The cathode is located on the right and is the spoon, which is made from inexpensive metal. Both electrodes are immersed in a solution of silver nitrate. Applying a sufficient potential results in the oxidation of the silver anode. Ag, letter 1D460 Ag plus, letter 1D44E letter 1D45E, plus E minus and reduction of silver ion at the spoon cathode. Cathode, Ag plus, letter 1D44E letter 1D45E, plus E minus Ag letter 1D460. The net result is the transfer of silver metal from the anode to the cathode. Several experimental factors must be carefully controlled to obtain high-quality silver coatings, including the exact composition of the electrolyte solution, the cell voltage applied, and the rate of the electrolysis reaction. Electrical current. Quantitative aspects of electrolysis. Electrical current is defined as the rate of flow for any charged species. Most relevant to this discussion is the flow of electrons. Current is measured in a composite unit called an ampere, defined as 1 coulomb per second, A equals 1 CS. The charge transferred, Q, by passage of a constant current, I, over a specified time interval, T, is then given by the simple mathematical product letter 1D444 equals letter 1D43C letter 1D461, when electrons are transferred during a redox process. The stoichiometry of the reaction may be used to derive the total amount of electronic charge involved. For example, the generic reduction process Mn plus letter 1D44E letter 1D45E plus Ni minus M letter 1D460 involves the transfer of N mole of electrons. The charge transferred is, therefore, letter 1D444 equals letter 1D45B letter 1D439, where F is Faraday's constant, the charge in coulombs for 1 mole of electrons. If the reaction takes place in an electrochemical cell, the current flow is conveniently measured, and it may be used to assist in stoichiometric calculations related to the cell reaction. Example 17. 9. Converting current to moles of electrons in one process used for electroplating silver, a current of 10. 23. A was passed through an electrolytic cell for exactly 1 hour. How many moles of electrons passed through the cell? What mass of silver was deposited at the cathode from the silver nitrate solution? Solution Faraday's constant can be used to convert the charge, Q, into moles of electrons, N. The charge is the current, I, multiplied by the time letter 1D45B equals letter 1D444 letter 1D439 equals 10. 23 CS times 1 HR times 60 minher times 60 SMIN 96. 485 C slash mol E minus equals 36. 830 C9 6485 C slash mole minus equals 0. 3817 mol E minus from the problem. The solution contains AgNO3, so the reaction at the cathode involves 1 mole of electrons for each mole of silver cathode. Ag plus, letter 1D44E letter 1D45E, plus E minus Ag, letter 1D460. The atomic mass of silver is 107. 9 G/mol, so mass Ag equals 0. 3817 mol E minus times 1 mol Ag, 1 mol E minus times 107. 9 G Ag 1 mol Ag equals 41. 19 G Ag. Check your learning. Aluminum metal can be made from aluminum, Roman 3, ions by electrolysis. What is the half reaction at the cathode? What mass of aluminum metal would be recovered if a current of 25? A pass through the solution for 15 minutes. Answer. Al 3 plus, letter 1D44E letter 1D45E, plus 3 E minus Al letter 1D460. 0777 mol Al equals 210 G Al. Example 17. 10 time required for deposition in one application. A 010 layer of chromium must be deposited on a part with a total surface area of 3m2 from a solution of containing chromium, Roman 3 ions. How long would it take to deposit the layer of chromium if the current was 33? 46A. The density of chromium metal is 7. 19G/cm3. Solution first. Compute the volume of chromium that must be produced equal to the product of surface area and thickness. Volume equals 0. 10 mm times 1 cm 10 mm times 3. 3 m2 times 10. 000 cm 21 m2 equals 33 cm3. Use the computed volume and the provided density to calculate the molar amount of chromium required. Mass equals volume times density equals 33 cm3 times 7. 19 gcm3 equals 237 gcr mol cr equals 237 gcr times 1 mol cr 52. GCR equals 4. 56 mol cr. The stoichiometry of the chromium. Roman 3. Reduction process requires 3 moles of electrons for each mole of chromium, 0 produced, and so the total charge required is. Letter 1d444 equals 4. 56 mol cr times 3 mol E minus 1 mol cr times 96,485 C mol E minus equals 1. 32 times 106 C. Finally, if this charge is passed at a rate of 33. 46 cs, the required time is. Letter 1d461 equals letter 1d444 letter 1d43c equals 1. 32 times 106 C 33. 46 C/s equals 3. 95 times 104s equals 11. 0 HR. Check your learning. What mass of zinc is required to galvanize the top of a 3 m times 5. 50 m sheet of iron to a thickness of 0. 100 m of zinc. If the zinc comes from a solution of Zn, no 3, 2, and the current is 25. 5a. How long will it take to galvanize the top of the iron? The density of zinc is 7,140 G/cm3. Answer. 11.8 kg Zn requires 382 hours.